Right. So feel free to interrupt and ask questions. It will also help me if the person who asked the question would also turn on their webcam so I can see who's talking. And feel free to also turn on your camera the rest of the time if you'd like. So hi everybody. Thank you for coming, and thank you, Hannes, for inviting me. My name is Uri Alon. This work is a joint work with Eran Yahav, who was my PhD advisor at the Technion in Israel. And now I graduated a few months ago and moved to Pittsburgh, Pennsylvania. And now I'm a postdoc at the Language Technologies Institute at Carnegie Mellon University. And this talk is about the bottleneck of graph neural networks and its practical implications. The main contribution here is that the recognition that GNNs suffer from a bottleneck that causes a phenomenon that we call over-squashing when trying to capture long-range interactions. Before we start, let me give you a quick introduction about GNNs that you all probably know, but let me just verify that we're all on the same page because there are different ways to think about graph neural networks. And in this work, I'll refer to GNNs as message passing networks, where every node has an initial representation, which is an embedding or features. And at every message passing step, which is a GNN layer, every node computes a message and sends it to its neighbors. And every node updates its own representation based on it receives messages and its own previous representation. So this is how a single GNN layer looks like. And we get a new updated representation for every node. And we can continue stacking layers and get more updated on node representations until after k layers, where k is usually a hyperparameter that is determined in advance, we get the final representation for every node with which we can perform node classification, graph classification, or any other task. Now, the thing that mostly distinguishes GNN types, or maybe the standard GNN types, are the exact functions of aggregating the neighbors and combining the neighbors with the node's own representation. So the general template is that the representation of the node V at time k or at layer k is a function of the same node V's representation at the previous layer, k-1, and the representation of all the nodes U that have direct edges to V. So the question is how to implement the function f. So for example, GCNs implement this by summing the neighbors and adding the representation of V itself, pass that through a linear layer and ReLU. Graph attention networks, GATs, perform a multi-head attention on the neighbor's U, given the representation of V as a query, and pass that through ReLU. GGNNs use a GRU unit that takes the node's previous representation and the sum of all the incoming neighbors. And finally, GIN performs a summation of the neighbors and add that to the representation of V times 1 plus epsilon and passes that through an MLP. And the reason why I'm telling you all this, because I want you to remember these summations in GCN and GIN. Each of them perform a summation of all of its neighbors. And we believe that this summation is harmful, even though it's good in theory, it's harmful when considering over squashing. And I'll talk about that later. I just wanted to remind you of the equations so you remember this summation. So what are GNNs good for? Traditionally, in the most common benchmarks, GNNs are good for short-range tasks like paper subject classification or friendship or collaboration prediction. So for example, imagine that we have two people, Alice and Bob, and each of them has 3 friends or people they follow on Twitter or academic collaborators. But for simplicity, let's call them friends in a social network. And now there's a new person called Carol, who is a friend of Alice. And the question is whether Carol should be a friend of Bob. And I think that in this case, it's very likely that Carol should be a friend of Bob because every friend of Alice is a friend of Bob. But notice that this this property or pattern that every friend of Alice is a friend of Bob is a very local property that requires only 2 or 3 message passing steps to learn. In this work, we argued that GNNs are not that good for long-range tasks, tasks that require learning properties that involve nodes that are 4+ edges away from each other. So to demonstrate a synthetic problem, that it's a synthetic problem, but it demonstrates like the worst case for oversquashing. So assume that we wish to predict a label for this target node. And I forgot to say that, imagine that we have a data set of graphs. Every example is a different graph of this general shape. And in every example, we have a target node that we need to predict a label for. And the correct label, the ground truth that we train the GNN to predict, is the label of the green node that has the same number of blue neighbors as the target node in the same graph. So in this case, the correct label is C, because the C node has 2 blue neighbors and the target node has 2 blue neighbors. So the GNN needs to pass the information that C has 2 blue neighbors to the target node and then predict the label C. Now, the problem is that in every example in the graph, we have a different mapping between alphabetical labels, A, B, C, and the number of neighbors. So it is not sufficient to learn this mapping once, because every example has a different mapping that needs to be propagated to the target node, and then the target node needs to select the right label. Okay, so in a global view, one second. In a global view, this is a simple problem, but in every example, the GNN needs to propagate all these alphabetical labels to the target node in order to predict the right label. Yes, Hannes, yes.
Okay, so we have a data set with a bunch of these graphs, and either we get it correct by, here in this case, predicting C, or we get it wrong, and then we failed at the task. And there are just many of these graphs in our data set, and we try to compute some accuracy.
Right.
Okay.
Right, that's right. And the accuracy is considered as 1 if we predicted the label C for this graph. But in another graph in the same data set, it could be that the C node had 7 blue neighbors and the target node had 8 blue neighbors, but there will always exist 1 green node that has the same number of blue neighbors as the target node, and that would be the correct label for that graph. So from the perspective of the target node really doesn't care about the rest of the graph. All it cares is that the rest of the graph may look like a tree where the target node itself is the root, and the root just accept incoming messages. So obviously, for the information from the node C to reach the target node, we need the number of layers to be greater than the distance between the C node and the target node. So the information would even reach the target node. So in this case, we need at least 4 GNN layers for all the information to be able to reach the target node. So at the first layer, information about C's neighbors flow into C, and we get a vector at the C node that holds the information that C has 2 blue neighbors. And then after 4 layers, this information reaches the target node, and the target node can see that the target node itself has 2 blue neighbors, and it just received the message that C also has 2 blue neighbors. So the target node can combine these 2 pieces of information and predict the label C. Now, the problem is that information from all nodes is propagated into the target node at the same time, not only this one branch of relevant information. And the receptive field of the target node grows exponentially with the number of layers. So initially, before applying any GNN layers, the target node is aware only of itself. After a single GNN layer, the target node receives messages from its direct neighbors. After 2 layers, the target node receives messages from the neighbors of its neighbors, until after 4 layers, which is what we need, the target node receives messages from all the nodes in the graph. So in other words, we wanted to flow a simple message to a distance of 4, but we had to squash an order of degree to the power of 4 messages into a single node representation, which is the representation of the target node. And this leads to a bottleneck at the target node and to a phenomenon that we call over-squashing, because an exponential amount of information is squashed into a fixed size vector. Are there any questions before we proceed? Because that's,
yeah. Sorry. Carry on, please.
Yeah, that's the main point. So I want to verify that everything is clear so far.
Yeah, I only had like a question regarding, so sorry, my name is Pierre. Yeah, I wanted to know something. Is it the case, is it this squashing over squashing, or this more particularly this exponential receptive field also applies when the graph is undirected? Because you would believe that that kind of exponential scaling behavior would also make it require less message passing steps, right? Because the information would go backwards and forwards. So I was wondering, like, what's your take on when the case is when the graph is undirected?
In general, it's the same case. So even if the graph is indirected and the needed information is at a distance of 4, you basically have the same situation where you need at least 4 GNN layers, and by having 4 GNN layers, you absorb information from an exponentially growing environment. So if it's a directed, it's an undirected graph, the situation might be worse, but the basic problem is basically the same.
Okay. Oh, yeah. I can see that the problem remains. Yeah. Okay. Thank you.
Yes, Dominic, please.
Yeah, so for graph neural network, the problem of over-smoothing has been studied in many different work before, where over-smoothing means that basically, because of this mean averaging that's happening with GCN or with GIN, it means that the graph reaches a sort of equilibrium where all the nodes have some kind of similar features. And for me, the way that you define the over-squashing is kind of, instead of looking at over-smoothing, which is a graph level view of the problem, the over-squashing is simply looking at a node level view of what is the problem. So in my opinion, I think like over-smoothing and over-squashing are the same thing, but with different observers. What's your opinion on that?
I have a slide about that at the end, so I would love to discuss that by the end of the talk, because I have a slide that tries to compare them, and I don't have a clear answer to are they the same phenomenon or not. I think that not exactly the same, but I'd love to discuss that, and I prepared a good slide about that. Yes, hi, Bo.
Hi, this is Bo. I don't think I quite get what the problem is. Can you go back to the last slide?
Yes, you mean this slide?
Yeah. So if we rely on label propagation to figure out the label of the target node, I understand what the problem is. But say that if we do subgraph sampling, where we sample the target node's one hop neighborhood, we also sample the label, the node with label C's one hop neighborhood. It seems that we can build a pretty good model to do the prediction, right?
Can you repeat how would you build the model to a better model?
Because so both nodes have 2 blue neighbors, right? So these 2 blue neighbors are the input to the function we want to approximate. So that's sufficient information to distinguish this target node from the other nodes, right? I don't understand why one hop sampling does not solve this problem.
Right. So what you're saying is that this problem can actually be solved by a non-learning algorithm. I could just write a Python function that doesn't use any learning to retrieve the correct label.
Sorry, I was
right.
not
I don't
clear.
need even to propagate any message.
No, we still do learning. What I meant is that we can just do one-hop sampling. So then the target node has two blue neighbors as inputs to that function, right? So the node with label C also has two blue nodes at the input. Then why
right,
can't
but they
we
don't have a
learn
direct
based
edge
on-
between them. Because they don't have a direct edge between them. So in standard message passing and graph neural networks, the information between them is not passed directly. If you take the entire adjacency matrix, then in a global view, you can see that. But in a standard message passing scheme, these nodes will not interact with each other.
Yeah, I don't want to hijack the discussion, but let me show you an example. So say that we have a mapping, and we want to learn a function to figure out what the mapping is. So the mapping is, if we have two blue neighbors, then the label must be C. That's a function
Right.
we want to learn.
Right, but in every example, this mapping is different. So the data set is composed of, let's say, 1 million examples, and every example has a different mapping from labels to number of neighbors. So the model cannot learn just the mapping. It must learn that it must learn to propagate information and make the decision based on the propagated messages, because the mapping changes between every example.
Yeah, so sometimes C has 2 neighbors, and in another example, C will have 100 neighbors.
Yeah. Okay, I'll think more about it. Thanks.
Sure. Yes, Namid.
I think this is a follow-on from one of the comments you just said, but this applies to standard message passing, but presumably you could have higher order or more advanced methods, especially things using attentional constructs, to potentially circumnavigate this effect. Maybe you go on to talk about that.
Yes, it's possible that higher order methods will solve that. But I think that at the same time, these higher order methods will also take into account more, the receptive field will grow as well.
Mm-hmm.
So it's possible that it will help, but if you take, for example, the neighborhood of size 2 instead of only the direct neighbors, then it will have more nodes in this receptive field to consider.
Okay, thanks.
Hi, Alessandro.
Hi, everybody. Alessandro here. Sorry, I have first a general question, probably obvious. So I was wondering if the dimension of the embedding in each layer is kept constant, or usually you increase or decrease. And a more specific question, hoping not to spoil your presentation, does increasing the dimension of the embedding may, let's say, ease the problem of over squashing? Thanks.
Yeah, so great question. In this case, we kept the dimensions constant across layers, but we did study the question of whether increasing the dimensions help, because intuitively you are right. Intuitively, if you have too many messages flowing into a small vector, then you can simply increase the vector. I'll give you a spoiler then, that increasing the dimensions is not enough, because you need to, the amount of information that is squashed grows much faster than the increase in dimensions. But I'll show a figure about that in a few slides.
Okay, thanks. But so in general, also for the other architecture, you keep the dimension constant over the following layers, or it's a good practice to reduce somehow?
In our experiments, we kept the dimension constant across layers. In general, I don't know if there is a general answer to that. In our experiment, we kept the dimensions constant. I agree that if you increase the dimensions, then it eases the over squashing problem. It's just that you get to the over squashing problem in longer distances. So if in this case you suffer from over squashing starting from a distance of 4, you can increase the dimensions, but then it will hurt you at a distance of 6, for example.
Okay.
But maybe in a few slides I show the figure and it will help.
Okay, thank you so much.
No problem. This is basically the over squashing problem. When an exponential amount of information is squashed into a fixed size vector, because we wanted to flow a message to a distance of, let's say, 4, but it forces us to squash an order of degree to the power of 4 messages. This is like the basic idea here. And actually, this is very similar to the bottleneck that existed in RNNs before attention, except that in RNNs, the receptive field was growing linearly with the length of the input sequence, while in GNNs, the receptive field grows exponentially with the number of layers. So the problem is even worse because it grows exponentially. But this problem also existed in RNNs before attention, because every decoder step had to squash all the information about the input sequence into a single vector and use this vector to decode the output sentence.
I had one more question, if I can.
Yeah, sure.
Yeah,
Sure.
so if you go back a couple of slides, yeah, one before. So what you are saying is here, when you have to predict, one more slide. Oh, or even this one.
This one?
Yeah. So if you have to predict the target nodes class, you pretty much have to, traverse like, diameter of the graph in the worst case.
Right.
Because the node that has the similar feature might be the farthest away from your target node. So you can't really do any algorithmic simplification there.
Right. This is the worst case. Maybe in some domains there are simplification assumptions, but in the worst case, I agree that you need as many layers as the diameter of the graph. Yes.
So that's essentially the exponential problem that you are saying, that you always have to deal with the diameter of the graph, the number of labels that you have to traverse.
Right.
Okay.
Thanks. Right.
May I also ask a question?
Yes. Yeah.
Would you agree that with your over squashing formulation, you are assuming that each node carries distinct information?
Distinct information?
Maybe an example helps clarify my question. What I imagine is, if you have a graph where each node feature corresponds to the label we want to predict, somehow a perfectly simple task, then the combination of exponentially much information, which is all equal and perfectly informative, is actually doesn't necessarily incur a squashing problem, isn't it? Because we have only one piece of information we want to fit in a finite size vector. Would you agree with this, or am I misunderstanding the over squashing concept?
Are you suggesting to include the number include the number of neighbors of the target node in the nodes nodes of the green nodes, if the representation of the green nodes?
Not directly. What I'm asking is whether it's true that the problem of over squashing only takes place if the nodes in the receptive field carry distinct information.
Is this true?
It is. The problem is, in the worst case, the problem is more severe if the nodes carry distinct information, right? If there are some redundant nodes, then yeah, maybe the problem is less harmful. In this example tries to capture the worst case of over-squashing. I agree that sometimes some nodes are irrelevant and maybe some nodes are identical. So maybe it eases the problem a little.
I would like to add on that, that the problem here is that at each GNN layer that you have, if you want to keep the information of all your neighbors accurately, you need to exponentially increase the size of your feature space for each GNN layer that you have. And even if there are some information that are irrelevant, the fact that not only you need to keep the message from all the neighbors that you aggregate, but you also need to understand also substructures and where the message came from, and not only what was the message itself. And in that case, it can easily cause, like, even if you have a very large hidden dimension, and even if you increase exponentially the hidden dimension, it becomes extremely hard for the network to remember that kind of information over long distances. So the problem of over-squashing, I think it really states the fact that if you want to send information between two nodes that are far apart, it's very difficult to do so because of this exponential increase of hidden dimension that you need to preserve the information from one node to the other. Unless, of course, you use some kind of attention mechanism. I think I'm spoiling the next few slides a bit, but yeah, with the standard GCN.
I completely agree. Thanks a lot for your answer. I actually read the paper in detail. It's very nice. Congratulations.
Thank you, and thank you, Dominic, for the explanation. I definitely agree with what Dominic said. So we wanted to see if this happens in practice. So we created a data set for every possible tree depth of this synthetic problem, and trained various GNN architectures on every data set separately. And this figure shows the training accuracy. So all the numbers here are training accuracy, not even test accuracies. And so the x-axis is the tree depth, the y-axis is the training accuracy, and every curve is a different GNN architecture. So the surprising thing here is that starting from a tree depth of 4, some of the GNNs could not perfectly fit the training data, no matter for how long we trained them and whether we used any optimization tricks. They simply could not fit the training data. In the paper, at the depth of 5, all GNNs couldn't reach 100% training accuracy. So even if some of them, like GGNN and GAT, could fit the training data at depth of 5, at depth of 4, at depth of 5, nobody could. In the paper, we show that combinatorially, to fit this data set, the dimension D, the hidden size, must satisfy this inequality with respect to the tree depth, such that there will be enough bits in the vector to compress all and express all the different training examples, because otherwise, from the pigeonhole principle, some different examples will result in the same vector representation, in the same compressed vector representation, and the model will not be able to distinguish between them at training time. So let's see how this inequality looks in practice. So this is the same inequality that I showed in the previous slide. The x-axis here is the tree depth, and the y-axis is the theoretically minimal required hidden size D. And as you can see, the hidden size grows very fast. And in practice, so this is the blue curve. Now, even if theoretically you need a certain amount hidden size, in practice you need even more, because even if a solution to storing to compress all the information in a vector of a certain size exists, it's sometimes very difficult to actually, for gradient descent, to find this, to actually find this solution. So in practice, the red curve is the empirical minimal hidden size that is required to perfectly fit the training data of a certain depth. So for example, you can see that at depth of 4, the minimal hidden size is 64. At depth of 7, the minimal hidden size is 512. So this means that 2 times increase, or even less than 2 times increase in message range costs 8 times increase in the dimensions. So this is referring to the question that I think that was asked by Alessandro, whether can we increase the dimensions? So here you see that you can increase the dimensions, but a 2 times increase in message range costs 8 times in the increase in the dimensions. So over squashing is only partially treatable used by only increasing the dimensions. We also found that different GNNs suffer from oversquashing differently, and specifically GCN and GIN suffer from oversquashing more than GAT and GGNN. We can see that at depth of 4, when we saw that GGNN and GAT could perfectly fit the training data, while GIN and GCN could not. Now, this is an hypothesis. We cannot prove it, but we think that the reason is that each GNN architecture's function. In GCN and GIN, every node in every layer performs a summation of all its neighbors. So it must compress all the neighbors into a single vector. In contrast, GGNN uses a GRU, which was shown to perform element-wise attention, and GAT uses a multi-head attention. So they don't need to actually imagine that each node has 2 neighbors. GCN and GIN must compress these 2 neighbors into a single vector, while GGNN and GAT can compress only some of this information. They are not forced to compress all the information into a single vector. Yes, Dominic.
I would like to ask if you experimented with the MPNN framework, where the receiving node and the sender node decide of a message. So basically, it's similar to GCN and GIN, where you do average or sum of the neighbors, but instead of having just summing all your neighbor features, the message is decided by both the neighbor features and yourself.
So this is basically like GAT, isn't it?
It's not like GAT, because GAT decides the weights associated to each neighbor, whether the MPNN decides the message that is sent by each neighbor, but then they are all averaged with the same weight. I think in some ways
I didn't try.
No, sorry, I just want to say, I think in some ways it can mimic GAT, and I was wondering if you have some experiments there.
I haven't tried, but I think I agree that I expect it to be similar to GAT. So the problem is that in all the first k-1 layers, in all the lower layers, information from the receiver node has no effect, because the receiver node must propagate all the information upwards. Only the target node, the label at the top, can provide any information about which information do we actually want. All the previous layers, all the k-1 first layers, no attention mechanism can help them deciding anything, because they just need to take all the information that is passed to them, compress it, and pass it upwards. So to your question, I expect that that it will perform similarly to GAT. In a more recent paper, we found that the reason is probably not the reason is the multi-head, not the attention itself. I'll show one slide about that in the end. I know that Hannes already presented this paper, but I just wanted to mention that I think that the multi-head issue is the key component in GAT here, in this case, and not the attention itself. And to give an intuition why GAT perform and GGNN perform better than GIN and GCN here, imagine the last GNN layer where we have the information from the two final gray nodes reaching the target node. So one of these branches is irrelevant because the solution, the relevant node of C, for example, is in one of them, and the other branch is completely irrelevant. Now, GIN and GCN must sum both incoming edges, even though one of them is irrelevant, while GAT and GGNN can select to absorb only one of these edges, and thus the effective bottleneck in GAT and GGNN is only half of the effect on GIN and GCN, and thus they succeed in a depth that is larger by 1. So this is shown in the figure that we saw before, where GAT and GGNN succeed in a depth of 4, while GIN and GCN succeed only in a depth of 1, or depth of 3, sorry. Now you're also probably wondering whether oversquashing happens in real life models, not only, so far we talked only about synthetic data sets. So we took off-the-shelf state-of-the-art models trained by others, and to break the bottleneck, we modified the original implementations of the authors and modified the last GNN layer to be a fully adjacent layer. I'll call it an FA layer, which is a layer of the same GNN type, except that every node has an edge to all other nodes. So the overall number of layers is kept the same. It's just that the last layer forgets about the graph structure and just propagate information from every node to every node. And I just want to emphasize, and then we retrained the model without adding weights and without any hyperparameter tuning. So we took the original hyperparameters without further tuning, retrained, and checked if that helps, if this simple solution helps. And I just want to mention that this is the most trivial idea, just to show that the bottleneck affects state-of-the-art models. I am not suggesting that using this FA layer is a good thing to do because it's extremely inefficient and it has a very high complexity of n² complexity. So I'm not suggesting that this is a good solution. I'm just showing that if this simple and maybe trivial idea works, then it means that we have a problem. So this is how it looks. So the K-1 layers are kept exactly the same, and only the last, the Kth layer, is a GNN layer of the same type as before, except that we changed the adjacency such that every node has an edge to every other node. So notice also that this doesn't add weights compared to the original model. It just adds more computation at training and test time. So this simple modification improves state-of-the-art GNNs without any tuning. And we tested it on a variable misuse dataset, on QM9, on NCI1, and the enzymes dataset. And it improved in all of these datasets. So let me show you 2 of these. So in variable misuse, the measures accuracy, so higher is better. So the blue bars here are the original results from Brockschmidt ICML 2020, where they extensively tuned dozens of configurations for every GNN type, and the blue bars are their results that they found. We took their implementation, their code, modified the last layer to be an FA layer, retrained, and got the orange results. So as you can see, the simple FA layer improved the results across all GNN architectures. This dataset also has another test set, which called the unseen projects test set. And in this test set, adding the FA layer actually decreased the accuracy in 2 of the GNN types, but it more significantly increased the accuracy in 3 other GNN types, and even got a state-of-the-art result for the RGCN. So I just want to mention how it's not just I'm not trying to say here are the state-of-the-art results for var misuse. It's not my point. My point is that even though Brock-Schmidt had tuned hundreds of configurations for this task, we simply improved it using a very simple trick. So my conclusion here is that no matter for how long they Brock-Schmidt et al. Fine-tuned GNNs on this data set, they still suffered from oversquashing. Yes, Dominic.
So here I failed to understand a bit the motivation of this FA layer. So one thing I noticed, for example, the fully connected layer for GCN and for GIN. For GCN, it would be simply taking the mean of all the nodes and summing basically summing it with a with a skip connection to the previous embedding, and then applying NLP. And for the GIN, it becomes taking the sum of all the nodes and adding it to the current layer. And this is something that was also explored by other works. They called it the virtual node, where you take this global representation and you mix it with the local representation. And here I was just wondering, like, how can we really say that this is over squashing and not the fact that each node has the opportunity to compare itself to the global graph representation? Because from what I see, like, it's more the second option, where each node compares itself, than really having over squashing, because in some sense, by doing a fully adjacent layer, all the nodes become connected everywhere, and you increase somewhat the over squashing because all the information of the graph is squashed together, and it doesn't really solve the problem of sending information from one node to the other node.
Right. So I agree that I forgot to explain what is the motivation for the FA layer. The motivation here is that we know that the structure matters, but we also know that using only the structure prevents some nodes in the graph to communicate with other nodes. So the motivation here was that the K-1 first layers would learn the structure, and the final layer will just allow nodes to communicate directly. So the final layer is for direct message passing between distance nodes, and the first K-1 layers are for learning the structure. I agree that it's not very clear how in the final layer, if all nodes are connected to all nodes, how that helps in GCN, for example. So I can understand how that helps in GAT. I agree that I do not fully understand how that helps in GCN, for example. But I also think that regarding what you said, that it's not only looking at the global structure, because theoretically, if you have enough layers, you can capture the global structure. So theoretically, you don't need the FA layer, because the global, if you have enough layers, the global structure will be propagated into every node, so the node would have this information. I also agree that, and maybe I'll show this slide now, I plan to show it later, but this idea was also found by previous work. So some previous work also broke the bottleneck by various means. So there was the super source edges and the virtual edges, and some papers added shortcut edges between nodes that the authors thought that needs to communicate directly. So I think that what happened is that all these papers had noticed that something is wrong, that something doesn't work, and they had the intuition that that long distance nodes are not communicating directly, and they needed another hack to solve it. But I think that none of these works explicitly framed it and said that this is a bottleneck and measured its effect. In all these works, it was kind of an additional implementation detail. So I agree that I think they found they felt over squashing, they felt its effect, but they didn't put a name to it and explain that that's the problem. They just solved it as if it was an implementation problem.
Yeah, I agree with your points here, but I think the difficulty is really attributing over squashing, like isolating over squashing in the problem and really saying that the fully connected attention helps. I think it's more like there's many reasons why the fully connected can work, and it's very similar to the virtual node and the super node ideas. And it's really difficult to pinpoint and say it's because of over squashing, because in my opinion, if over squashing was the problem, then instead of using a fully connected attention as the last layer, you should always use a fully connected transformer at the so that two nodes that are very far apart can communicate the information. Because here it's not about
it's basically the same thing.
Communicating. Yeah, so basically the same thing as you did for the GAT, but like the same layer as you did for the GAT, but for the GCN and the GIN. And this can basically better show that the information sending between two nodes that are far apart is important, and not simply the global representation of the graph that is important.
I agree that we can't pinpoint the problem. We can't tell for 100% certainty that the reason why FA layer works is because over squashing. My main point here was to show that we have some problem. Maybe I think that it's the over squashing problem, but if such a simple solution helps these extensively tuned models, then it means that we have a problem. Some problem. I can't be 100% sure that it's over squashing, but the fact that a simple solution simply improves these results is problematic. Hannes, do you have a question?
Yeah, like my comment is or question is very much along the line of what Dominique said. And like I saw your QM9 experiment and your VAR misuse experiments kind of as evidence that over squashing is not the problem, because we can see that that if we don't use attention, that we should have over squashing if we don't use attention, but we still get the improvements, right? So the improvements don't come from avoiding over squashing.
I think that even GCN or GIN, even though they don't have an explicit attention, when you connect distant nodes, even if it's with a GIN layer, they do perform an interaction, even if it's not an attentive interaction, they do interact directly, and you do save the problem of that messages are compressed over distance. So the problem of over squashing is basically that messages are compressed and noised over a long path. And by adding the FA there, you save the long path and you allow nodes to interact directly. And I think that this direct interaction is what helps over squash in this case.
Okay, so
because basically GIN is a universal approximator. It can mimic attention.
So you're saying that over squashing is not really if we're, for example, aggregating from all of the nodes at the same time, and then we can't have all of that information in the single vector, but instead over squashing means that we aggregate from many nodes and have to additionally propagate that information through multiple layers and through multiple steps.
Right. That would be a more accurate description, because if the path is short, if the path is just one edge, then I think that GIN, for example, can mimic the attention and interact with nodes directly.
Okay, and then I also wanted to ask something from the chat. Can oversquashing be mitigated by using something like jumping knowledge layers or skip connections as well, I would guess, but that's not the case, right? Like if we, in the last step, just aggregate the nodes of, we just sum up, or yeah, we aggregate the nodes of all layers instead of just the last GNN layer.
Oh, no, okay, I understand the question. So aggregating the nodes, the same node from the previous layers, which is skip connections, would not help, because this is a different axis. This is the layers axis, where we are interested in the distance axis. So these are not the same axes. I would like to continue, so because we're kind of short on time, I planned this presentation for a shorter time, but I'm so happy that there are so many questions. Let me just show you a few more slides, and then we can continue asking questions. I have plenty of time after this meeting. So here are the results in QM9 across all different examples, as Hannah said. Across all different architectures, adding the FA layer improved the results. So here, lower is better. So decreasing the error is an improvement, and the FA layer improved the error by about 40%. We also wondered maybe the number of layers simply wasn't enough, and maybe the important nodes were distant, and the receptive field of the node on the left was this red circle, and the receptive field of the node on the right was this circle, so they don't interact directly without the FA layer. And maybe all the FA layer did was just connecting nodes that previously were not getting each other's messages. So to verify that, we call this underreaching, where the number of layers is not enough to contain to send all the messages that need to be sent, where the number of layers is lower than the graph diameter. And specifically, in this data set of QM9, the number of layers that we use was 8, and we checked the diameter, which was 10. The maximum was 10. On average, it was 6, and the 90th percentile was 8. So first of all, it means that 90% of the examples did not suffer from this underreaching, because every message could be sent theoretically to its destination. But we also tried to increase the number of layers to 10, such that all the examples in the data set would be able to, would not suffer from underreaching, and it didn't help. We also tried to increase the dimension, as was suggested by Alessandro before. We increased the hidden size by 2, and it resulted in only a 5% error decrease, where adding the FA layer resulted in decreasing the error by 40%. And this is maybe expected given the figure that we showed before, that showed that the hidden size needs to be increased very quickly with respect to the depth. I also want to show you a comparison between oversquashing and oversmoothing, and maybe we'll just discuss it afterwards. So this is a very the question that Dominic asked, whether oversquashing is oversmoothing, is very common. I'm asked that a lot. So let's denote by R the problem radius, the required range of interactions between nodes, and denote by K the number of GNN layers. I believe, now I will be happy to discuss it, and maybe I'm wrong here. I believe that oversmoothing happens when the number of layers is much higher than the range. For example, if we have this triangle graph where the range is only 1, but you have many more layers than 1, then node will go indistinguishable. Underreaching is the easy case, where you simply don't have enough layers. So for example, if the needed range is 4, but you have less than 4 layers, no matter what, the GNN cannot fit long-range patterns. And oversquashing happens, I think, when you do have sufficient number of layers and the radius is, sorry, you have sufficient number of layers, not too few and not too many, but both of them are just high. So for example, R equals K equals 4. So theoretically, you are able to fit the data, but the GNN just fails to fit these long-range patterns. Just one last quick note. I told you that GAT performs a multi-head attention. So if any of you hadn't seen Hannah's presentation about this paper, in a recent paper, we show that the attention in GAT is actually very, very limited. If you have a set of query nodes and a set of key nodes where every query node is directly connected to every key node, the only pattern that GAT can learn is this pattern where there's a single key that gets all the attention, no matter which query is it. And by that, I'll just skip to the summary. To summarize, to pass long-range messages, we need many GNN layers. The problem is that the receptive field grows exponentially with the number of layers. And this leads to a bottleneck and oversquashing, which prevents GNNs from fitting long-range patterns in the data. We found that GCN and GIN suffer from oversquashing more than other GNN types, and that state-of-the-art models can be improved by considering the bottleneck. And finally, regardless of the bottleneck, GAT v2, which is the solution to the attention problem in GAT that I talked about in the previous slide, is now part of PyTorch Geometric. And I encourage you to use GAT v2 instead of GAT, whether comparing to the standard baselines, or if you have a large model where the GNN is a small component, if you switch the GAT component to a GAT v2 component, you get a strictly more expressive GNN, and it is part of PyTorch Geometric. That's it. I'd love to take questions, and I can stay here for as long as you want.
That's lovely to hear. Okay, then, well, yeah, let's just go with Dom.
Yeah, thanks, Hannes. And thanks a lot, Gori, for the presentation. It's a very good presentation, and I really like how you explore the concept of oversquashing, where the literature was mostly focusing on oversmoothing. You kind of identified a problem that is somewhat related but not identical. So thanks a lot there. One thing I would like to ask is that there has been many recent work that explored the positional encoding, and especially, like, I think a recent work that was published 2 or 3 days ago from Vijay Dwivedi, Xavier Bresson, that explored, for example, how positional encoding allows gated GCN to perform much better than without any kind of positional encoding. And here, for example, you also show that GAT does not perform very well. I'm not sure what's the GAT v2 exactly, but there has been also some work showing that how positional encoding can really help GAT perform better. So my question here is, how do you think using positional encoding, like any kind of positional encoding, can help mitigate oversquashing? And do you think that the newest work go in the right direction in mitigating that problem?
Okay, so I haven't read the paper that came out 2 days ago, but it depends. If your positional encodings, if you add some sort of positional encodings, and then you forget about the structure and let every node communicate with every other node, then it might solve the problem, as in transformers, actually, where the positional encodings are in the first layer, and in the following layers, every node, every word in the sentence can communicate with every other node. The problem in graphs is that it will be very expensive to let every node communicate with every other node because sometimes they are very huge graphs. So I think that is a possible way to solve oversquashing by introducing clever positional encodings, but then let all nodes communicate with all other nodes. If you don't let every node communicate with every other node directly, and you just keep the message propagation on the same graph structure as in the original graph, then I don't see how it will solve oversquashing because the same phenomenon will happen where messages will be passed over these edges, and you'll have an exponential amount of information squashed after every layer. So I think that something that does connect all the nodes and introducing the structure of the graph in another way, such as positional encoding, might help, yes. Yes, Hannes, you want to ask a question?
Yeah, I wanted to let Johannes go first because he's more on the left, but then can we, or what do you say about, or can we go back to your to the graph where you show the number, the dimension going up and the yeah, exactly.
Yes.
So here again, I would kind of see this as evidence against over squashing, because we would expect the if it is really just over squashing that's causing the problem here, then I would expect the red line to be on top of the blue line, or maybe right of the blue line. But now we see that if we increase the dimension and should in theory alleviate the over squashing problem, we're not alleviating as much if we as we would expect if over squashing is really the main problem.
Okay, first of all, the red line cannot be to the right of the blue line, because the blue line is the theoretical lower bound. So everything must be above the blue line. In practice, there is a gap between them, because even if theoretically you could engineer the weights of the GNN to encode all the information in a certain way, it's not always learnable, and gradient descent will not is not guaranteed to find that solution. And also optimization doesn't work on the bit level; it works on a float level. So the blue curve isn't really reachable.
Yeah. Okay.
The red curve is the practical one, and to me, what it shows is that increasing the dimensions can help, ease over squashing. It's just that you need to increase the dimensions by a lot. If you want to solve the problem of 7 layers, you need a 512 hidden size. So solving the problem for a depth of 8 will require a much higher hidden size. So increasing the dimensions is a possible solution, just limited.
Yeah. Johannes, you want to go ahead?
Yes, thanks. Sorry, my computer doesn't let me turn on my camera today, so I'm not deliberately going against the suggestion. I wanted to ask, in statistics, there's this concept of the James Stein estimator, which is a bit surprising. It says that in a multi-class classification task, so if we have more than 2 classes, shrinking all predictions towards the grand mean dominates the standard predictor. So performance is improved by shrinking predictions towards the population mean. Have you explored the relation of your fully connected layer to this James Stein phenomenon? Because they might be related. Do you agree, or?
I actually have no idea. I'm not familiar with this phenomenon. If you can send me a reference or a paper or something, I'll be happy to read it, but I've never thought about this.
Yeah, sure. I can email you.
Yeah, sure, of course. I'll show you my email. Yeah.
Essentially, I think it might be a statistical effect that you're observing with the fully connected layer, but I didn't look into this in detail. Thanks.
On the chat, I didn't follow the chat, but Chinmay says that it would be great if you can put it in the chat, Johannes, the reference to the statistical phenomenon, not only emailing to me.
I don't have a great reference, but I can post the Wikipedia article or something. It's I don't know,
yeah,
30, 40 years old or even older. It's called the James Stein estimator. I'll see whether I can quickly find something to put in the chat.
Right. Any more questions?
Okay. I guess not. But then I just want to say a last thank you, a very big thank you. I mean, I think this was an especially awesome discussion and especially awesome presentation. And yeah, also not just thank you to Uri, but also thank you to everyone who asked this many nice questions.
Yes, thank you, everyone. I really enjoyed this. I think this is the talk that about this paper. I gave several talks about this paper, and this one is the one that I enjoyed the most, thanks to your questions. So thank you.
Okay, that's very nice to hear. Were the other the other talks more talk like and less discussion like? Or
yes, there were less discussions because there were less discussions and less questions, and
yeah, I think but it's also in big parts due to you, because you allow these questions and set them up so nicely. So yeah.
Hi, Uri, sorry, last minute.
Yeah,
I had one more question. So going back to your slide, I really didn't understand why even when k equals r, adding the last fully connected layer helps. Even when k equals r. What's the intuition behind that?
Just a second. Trying to. So you're asking in general why the FA layer helps?
Yeah. So you showed that squashing happens in the regime when k is much larger than 1 and similar to the close to the diameter. So even if k is equal to or a little bit greater than r, why adding the the last layer that you suggested helps? What's the intuition there?
The intuition is that it allows the green node at the bottom to interact directly with the node. It allows the recipient of the message and the sender to interact directly instead of the message being squashed over distance, over a long path. And I believe that by allowing them to interact directly, this is partially solves the over squashing. But it's not a practical solution anyway, because the FA layer is just it has an n squared complexity. So it just was meant to
let's forget the complexity
demonstrate that there's a problem.
Yeah, let's forget the complexity for a moment. So why for example when you receive the information from all the nodes, okay,
right,
are you saying that the farthest nodes from this target node has some information or has accumulated the features that it has got by this because of the large number of layers, and then it needs to propagate that information, and that's the FA layer is helping that?
I think that once you have the fully adjacent layer, if you have an expressive enough GNN, then it becomes a question of the expressiveness of a single layer. You have all the information flowing directly inside the target node. So a function that takes the target node and the sum of all the neighbors, if this function is expressive enough, it can take all this information and pull out of it only the relevant node. And oversquashing happens when you compress the information over a distance.
Yeah. So what I was thinking, let's say your problem set has a length scale. Your diameter is R here, right? The R is the diameter, and your length, is it R is the same as a length scale? Or are you treating them as the same?
Is R the same as what?
What is R? R is the diameter of the graph, or is it the length scale of the problem?
Okay, so R in general, I referred to R as the problem radius, the needed number of layers.
Yeah. Okay. The length scale of the problem.
In this case, it's also the diameter.
Okay.
Yeah.
So let's say
yeah.
So let's say we have two different, R is the length scale of the problem. Let's stick with that. D is the diameter of the graph, which is probably greater than R, and your number of layers is K. Okay. And if you choose, for example, K to be, around 2R, okay, twice R, do you think you need the FA layer, or would it pretty much solve the problem that the FA layer is solving?
I don't know. I think it depends on how large them. I actually don't know. I even don't know if this slide is correct. This paper was meant to show that there is a problem. I don't know yet how to solve it and whether different possible solution will solve it or not. So
yeah, my intuition was that if R is a length scale of the problem, we need to propagate for at least that many layers for all the nodes to get the relevant feature. And then basically you need another R layers to propagate the information from any node to another node. So
right,
and that's what the FA layer is short-circuiting.
Yes, so theoretically, if you take 2R as your number of layers, then theoretically it could help because it's like as if the recipient of the message would broadcast that its number of layers and would ask the other node for the information that it needs. And then in the next R layers, this information would be sent back to it.
That's right.
So it is if the target node requests the information and then it gets it back. So theoretically, yes. The problem is that even nodes that we don't want to broadcast their information always broadcast their information in every layer. We can't shut some nodes. So maybe with a more clever architecture that have a gate for every node or every edge, this can be solved by setting K to R. Yes.
Okay. And the FA layer is kind of short-circuiting that. Once you have accumulated the right information, you just broadcast it.
Right.
Okay. Thank you.
Thank you. Yes, Dominic.
Yes, sorry for the late question. I would like to go back to my original point that oversmoothing and, in my opinion, oversmoothing and oversquashing are the same phenomenon, but from a different observer. Here, I believe
possibly.
Yeah. So here, I believe it's a bit a simplification of having this K much greater than R and K equal R. Because yes, oversmoothing means that nodes will be indistinguishable when K is infinite. But I think oversmoothing is more the problem that even when K is a finite and small number, you destroy the high frequencies, the high frequency signal in the graph. Whether oversquashing is the inability of sending information from one node to another node. And one can view sending your information to another node as sending kind of a Dirac signal of your own information, or kind of a very high frequency signal, a very high frequency pulse from node A to node B. And when you look a bit at spectral theory, basically the inability, the fact that if you want to send a signal from node, a pulse from node A to node B, the node B will receive a smoothed Gaussian, is very similar to the idea that oversmoothing means that high frequency gets destroyed. So that's what I want to say from my point, that oversmoothing is oversmoothing and oversquashing is the same thing, but from a different observer. And another thing why I think that is, I don't believe there is any solution for oversmoothing that is not also a solution for oversquashing. Yeah, so what's your thought on that?
I agree. I don't know, and I must admit that I'm not, and I don't know enough about theory of frequencies and pulses, so I don't think about GNNs in that way at all. But what do you think about the example of oversmoothing here? If you have a problem that can be solved using one layer, or maybe some number of layers, and you have too many layers, isn't this an example of oversmoothing? In the left column?
Well, in theory, the network could learn, could solve the problem with the number of layers it needs, and for all the other layers, just have all the weights to 0 and use the residual connection to propagate the information. So in some sense, I'm not sure about that.
So can I add a comment here? So I think, Dominic, what you are suggesting is oversmoothing and oversquashing are basically in two, what they call conjugate domains. Oversquashing is in the space, linear size domain. Oversmoothing is in the corresponding, momentum domain. Is that what you're thinking? Because here it looks like oversquashing is basically, I have instead of a wide highway, I have a narrow highway, right? So I am not able to provide enough information through. But oversmoothing is basically, I'm just in the opposite, like in a conjugate domain, I'm not able to pass the high frequency information. I'm just only, in the end, becomes a low pass filter.
Yeah, this is a good way of thinking about it. Yeah.
So maybe, one can't really solve both at the same time, and there has to be some mitigation, right?
So why do you think we can't solve both at the same time?
Oh, I'm just looking at it very from if these are basically conjugate, variables, right? There is a, in physics, there is something we call uncertainty principle, right? So I'm thinking along those lines.
Yeah, but I don't think the uncertainty principle of that is in physics applies here. I think the uncertainty principle is really a quantum property. So I think here the fact that because the uncertainty principle is like the position and the velocity of a specific quantum particle cannot be determined, and cannot be determined because the two are conjugated together in some sense. But here I don't think it's the case, because as soon as you have as soon as you're able to send information, suppose you have a perfect graph transformer that works perfectly, that doesn't have oversmoothing, that is able to send the right information to the right node in a perfect way. well, you don't have oversmoothing, you don't have oversquashing, and at the same time, you don't have oversmoothing because the information is sent exactly in the right way. So I don't think it suffers from the uncertainty principle. But I think your observation that one is kind of the frequency domain, how we oversmoothing is how we can think of the problem in the frequency domain, and oversquashing is how we can think of the problem in the spatial domain. I think it makes sense.
Yeah, thank you. Thank you.
There's
someone.
Still...
Someone called V raises their hand. I don't know who is it.
Yeah, apologies. I think Zoom just picked up my initials. Following on from this physics sort of analogy, I was wondering if you've explored the idea of sort of this information flow or flow across these graphs. Because if I understand correctly, what you're saying is you will lose, because of this compression as you go along in length, you will lose some of the information that's required. Whereas, if I understand your idea, but your distinction between squashing and overfitting, whereas if you're oversmoothing, then this information is sort of going to be pushed towards a normal, so some sort of normal distribution. So one is akin to information loss, whereas the other is akin to sort of normalization or being pushed to a particular pattern. And I was wondering if you've done any sort of analyses along this sort of graph flow, information flow on networks sort of idea.
No, so I agree with your intuition about information loss and information shift. I haven't done anything, and I think I don't have a good enough understanding of the theory. I saw that on iClear now there is an anonymous paper under review that tries to explain oversquashing, and I haven't read it yet, but it will be interesting. I can send the. It's called Understanding Oversquashing. Are you doing? Hannes, do you know which paper I'm talking about, right?
I'm pretty sure.
Okay, so yeah, I don't have a good answer. I would love to read more papers that that's the paper. I would love to read more papers that try to analyze and explain that, because I don't have a good enough understanding.
Okay. Thank you. One more sort of follow-up from that. If we were to sort of inject, so have an input of noise, like you take the features and you inject noise into this graph thing, what do you think the impact of the FA layer would be? Just I mean, I understand it's a bit of a stretch, but just intuitively. And perhaps the motivation behind me asking that is, if my initial understanding or my initial analogy is correct, I would imagine that the FA layer, the FA layer would give rise to a certain type of shape, output shape from this noise in the features, whereas the sort of squashing problem would give a different sort of shape. Perhaps I'm not explaining myself as clearly as I would want. So suppose you injected noise into this network. So your entire input is just pure noise, white noise. What would the output signal look like after adding this FA layer on each one of, let's say,
I have no idea. So what are you suggesting that how it would look like?
So if it looks completely normal, for example, right, then we know that that's what happens in sort of this smoothing type of thing. Whereas if we see the shape of the noise, so if it's just a loss, right, we would imagine that the noise looks the same. It still looks pretty much uniform coming out of it. And there are ways to do this more sophisticatedly, so in a more sophisticated way. So you could like subtract or factor out. You might be able to factor out what you'd imagine the shape of the noise would be from the signal on the graph. Again, I think that might be going back to the frequency sort of thing that that was being discussed earlier. But I just wanted an intuitive idea. Yeah. But thank you.
Thank you. Yeah, it's an interesting direction. Yeah.
So what you are saying is, how can I filter out the noise at the receiver at the target node?
Well,
how the distribution of the noise looks like, right?
Yes. So in some sense, I don't want to filter. Yes, I do want to filter it out, because if my hypothesis is that noise due to over smoothing looks normal, for the sake of argument, let's say it looks normal. In that event, if I can factor out, or I can modify the signal so as to take that out of it, then I can see what is the actual over squashing component of this thing, right? So I can, in some sense, tease apart those two factors, and then we can say what is over squashing and what is over smoothing.
Yeah, I agree that that's very interesting, and I would also like to get more understanding of that, because we wanted here to kind of highlight the problem, and even though we don't fully understand it yet. Okay.
Yeah, but it was, thank you so much. It was a very interesting and very stimulating presentation, especially with the discussions and everything.